Okay, so in this video, we're going to talk about hydroelectric power, which is going to be the very last topic or the very last concept that we're going to talk about in 8.1. And if you think that you might have missed everything that was in the unit, I would refer you back to chapter 8.1 in your IB physics textbook. Okay, so when we talk about hydroelectric power, in the context of the IB curriculum, we're typically talking about what's called pumped storage. Now, technically speaking, you can put like a water wheel in a river and have that, turn the water wheel and generate electricity that way. That's not the type of hydropower we're going to talk about. We're actually going to talk about what's called pumped storage, which essentially what we're talking about is like a dam. And so basically, up to this point, every energy source we've talked about is what's called a base load station, meaning that it operates 24/7. Okay, so whether that's a nuclear power plant or fossil fuel plant, natural gas plant, coal plant, any thermal power station, but also solar power and wind produces energy on demand. When we talk about pump storage, we're not necessarily talking about something that's producing electricity every second of every day, but it is, as the name implied, a way to store energy. In the event that power demands are greater than the available supply, for example, in the winter storm we had a few months ago, you can use a pump storage plant to make up the deficit. Now, in that case, our energy needs in the state of Texas were so high, I don't know that any pump storage plant would have really helped, because the demand was so great. But theoretically speaking, in the event that power demands are greater than the available supply, you can use a pump storage plant to make up the deficit. The way a pump storage system works, and it's really important that you understand the concept because a lot of problems, kind of like the specific energy calculations we did before, a lot of the problems don't necessarily use a set equation. You kind of have to use your reasoning skills and your problem solving skills to answer certain questions, um, assuming that you know the basics of how these work. And so the basic way a pump storage system works is that it uses the gravitational potential energy of the water held at a high level, and that energy transfers to power generators. Okay, and so just to kind of recap, when we talk about gravitational potential energy, we're talking about, EG, we're talking about M, G, H, and all of that kind of thing. Okay, so really it's the water being stored at a height and then having that energy as the water flows down to a lower height, it loses the gravitational potential energy, and the idea is that some or most of that energy um, goes to electricity. Of course, you always have energy degradation, as we've seen, but the idea is that most of that energy would be transferred to electrical energy by turning turbines and generators. Okay, so to get a visual, this is basically what a hydroelectric dam might look like. And so the idea is that sun-driven evaporation and rainfall put water at a high potential energy. And so these can be, man-made or not, but the idea is that the sun, evaporates water, it rains, the rain over time fills what's called the reservoir, which is where the water is held. As we'll talk about later, it's also possible to pump water back up into the reservoir for later use. Now, you might ask, well, hopefully you might ask, doesn't it take energy to pump water back up? And actually, doesn't it take more energy to pump the water back up than you get um, when you release the water and the water goes down? And the answer is yes. And so a hydroelectric dam, or this pump storage scheme, is not a way to create new energy. In fact, it uses more energy than we actually get out from it. So what's the point then? If it uses more energy than it's worth, then why do it? Well, it's basically like a giant battery. It gives us a very convenient way to store energy for when we might need it later. Okay, even though getting the water back up, assuming we pump it back up, is not efficient, it's convenient in the sense that it's kind of on-demand energy. Right, and so you can see from the picture here, when there's a high demand, they can lift this up and the water can kind of flow down here, and there's a turbine connected to the generator, and it turns and the water flows down into the river and the generator produces electricity. And then eventually either they can pump water from the river back up or they can just wait for the sun to evaporate some water and have it rain and whatnot. Okay, and so here's the same basic picture, and there's a picture of what it might look like. And so if you think about the energy transfer happening in this situation, we basically have the gravitational potential energy of the water that changes into the kinetic energy of the water as it goes down, and then the kinetic energy of the water, of course, goes to kinetic energy of the turbine. The spinning turbine produces, or the spinning turbine, which is connected to the generator through electromagnetic induction, produces electrical energy. And so that's roughly what the energy flow diagram would look like um, for this type of system. And I think we've already talked about this. All right, so let's get to doing some calculations. Because these types of problems rely on gravitational potential energy, we can do some things to calculate the maximum power P available. Now, I'm going to go through some things, but there's some principles that you really need to understand. And you also need to understand that sometimes you see a problem that you've never seen before. It's talking about quantities that you don't recognize, and you just have to use problem-solving skills to figure it out. There's no like magic formula. There's nothing in the data booklet having to do with this. It all comes down to, at the end of the day, it all comes down to gravitational potential energy and using that equation in some way to answer the question. All right, and so just a couple things. As the water falls, the mass of the falling water is going to lose gravitational potential energy equal to mg, what I call here mg delta H. Okay, or when I say delta H, I just mean that the height that the water flows through. Now, something else I want to point out, when you talk about the height of the water, it's not so obvious exactly which height you should use. Because let's say this is like, the reservoir, and let's say this is the water level, and let's say the height of the reservoir is h. All right, so what height do you use in that situation? And the obvious answer is, well, you use h, right, because it's mgh. But you can't use mgh here because um, h is the height of the highest point of the water level, and most of the water is actually less than that. Okay, and so if the height of the uh, reservoir is h, the height you would use in the calculation equation would actually be h over 2. Okay, you would basically use the average height, or the midpoint height, however you want to think of it, as the h in your calculations. Because if you use half of the height, then on average, half the water is above that height and half is below that height. And so that's a good value to use. Whereas if you just use the total height, most of the water is less than that height, and so it's not an accurate. It would make your calculation inaccurate. Okay, so just kind of keep that in mind. So starting with this premise, to go from energy to power, remember power is energy over time. And so what happens if I divide by time on the left side, I get power. But if I divide by time on the left side, I have to do the same for the right side. And so if you look mgh over t, there's a couple different quantities I want to point out to you. And which ones are important depends on like what you're given in the problem. Every problem is going to be different with pump storage problems. Okay, again, there's not like a set equation to use other than starting with the mgh equation going from there. All right, so first of all, I want to point out that if you have mgh over t, then you could actually group this in a way where you have m over t times gh. Now, when would you need to do that? Let's say you knew how many kilograms of water were flowing per second, then it would make sense to group those things together. Okay, is that going to be the case in every problem? No. But if you're doing a problem where it says like this many kilograms of water flows per second, then it would make sense to group it that way. Okay, and I'm just trying to give you advice based off of what I've seen in past problems. Another thing I've seen in past IB problems is instead of giving you like how many kilograms of water is flowing per second, they actually give you what's called the volume flow rate. Okay, and so I've actually seen them give you like the density of water and what's called the volume flow rate. And remember, density is mass per unit volume. And so the mass of the water would be the density of the water, which is typically given. And if it's not given, it's 1,000 kilograms per cubic meter. And so I've seen some problems where you need to replace a mass with density times volume over T times G times delta H, where they might give you what's called the volume flow rate. That is how many cubic meters of water is flowing per second. Okay, and so this is not like a set equation or anything like that because every problem is going to be different. But I'm just trying to give you some tools that you could maybe think about using when you're doing different types of problems with pump storage power. All right, so pause there, make sure you add that to your notes. We're going to look at 2 examples with calculations before we move on. Okay, so let's look at this problem that is in the PowerPoint. So it's kind of a crude picture, but bear with it. So it says a reservoir for a hydroelectric dam is shown. And the first question says calculate the potential energy yield. All right, so we have what looks to be like a rectangular thing of water. And so we want to know what is the potential energy yield. What type of potential energy is this talking about? Well, obviously gravitational potential energy. And I know that is mgh. Now, okay, so how do I get m and how do I get h? Well, h we talked about before. Remember, when you're talking about the height of a body of water, you're not using the maximum height. You're actually using kind of the average of that reservoir. And so here, if you see from the lowest point to the highest point is 125 meters from here to here. If you go from the ground to the bottom of the reservoir, that would be 75 meters. And neither of those heights are what we should be using. We should actually be using the midpoint of the height of the reservoir itself, because remember, if we use the midpoint, then half of the water is below that height and half is above that height. And so what we actually want to do is 75 plus 50 over 2, which is 100 meters. Okay, so that's the height we're going to use later on in the problem, just to kind of keep that in mind. Now, we're given the dimensions here of the water, or I should say of the reservoir. And so I can find the volume by just doing, 1700 times 2500 times 50. It's just like a rectangular prism, 1700 times 2500 times 50. And I get, oh gosh, a big number, 0.00000 cubic meters. Now, what does volume have to do with mass? Well, density is mass over volume. And I said before, if you're not given this explicitly, you can assume that the density of water is 1,000. Okay, so if the density of water is 1,000 and the volume is this giant number over here, I don't even have room to write all those zeros, then I can calculate the mass of the water. And you know what? I'm just going to do scientific notation actually. Multiply that by 1,000, and I get 2.125 times 10 to the power 11 kilograms. And then I can find out how much potential energy that is because I have the mass of the water. I have G, which I'm just going to use 10 for G. And then the height is not 75 and it's not 125, it's 100 meters. Okay, and so if I did that correctly, I should get 2.13 times 10 to the 14 joules of energy available. Hopefully I did that correct. Yes. All right, so that is the gravitational potential energy stored by the average amount of water inside the reservoir. And of course, some of the water has more energy than that, some has less, but that's the value I'm going with, because that is the potential energy yield. So that means theoretically, if the process was 100% efficient, that's how much energy I could, get out of this dam if I completely emptied it. And of course, that's not going to happen. All right, so pause there, before I go to part B. Okay, part B says, if the water flow rate is 25 cubic meters per second, what is the power provided by the moving water? All right, so power is energy over time. And I know that the energy here is gravitational potential energy. So this is kind of what I'm thinking of as far as the equation goes. All right, but this form of the equation doesn't really help me because they're not giving me, you know, mass, they're not giving me time, they're giving me this volume um, of water is flowing per second. So I need some way to connect that back to mass. So remember that density is mass over volume. And the density of water is 1,000. And so let's say if the volume flow rate is 25 cubic meters per second, then that means in 1 second, the mass of water that flows would be 1,000 times 25. Right? In other words, in 1 second, if it's 25 cubic meters per second, that means in 1 second the mass would be 1,000 times that because the density of water is 1,000. So that's 25,000 kilograms of water per second. Knowing that, I can answer the question, what is the power provided by the moving water? Because I now know m over t is 25,000. And so that would just be 25,000 times 10 times the height. And remember, the height I'm using here is 100. And so that would be 25, let's see, 1,000, add a 0, add 2 more zeros. Okay, so that would be, let's see, 25 million watts. Or I guess it'd be easier to write 25 megawatts. All right, so that is part B. Pause it there if you need to look at that some more. And there's a word for that problem. And then finally, C says, if the water is not replenished, how long can this reservoir produce power at this rate? So obviously, if water is flowing out, eventually it is going to run out because the thing only stores so much water. And so let's kind of think about this. And I, I want to be really clear. I'm not using any magic equations. I don't have anything, any like super secret equations, anything. I'm just trying to reason out what I know about the situation. The only equation that is fundamental to doing these problems is the MGH equation. Aside from that, everything else is just problem solving. And so I just need to figure this out. I know that 25 cubic meters is flowing out per second. And I know it's going to keep flowing out until we run out of water. All right, so this is volume per second. So basically, if I think, what is the total volume? And then I divide by this rate, then I can find the time. So in other words, the rate should be equal to the volume, the total volume per unit time. All right, I know the rate, and actually the volume I found at the beginning, because that's just 1,700 times 2,500 times 50. And I remember that was a big number. 1,700 times 2,500 times 50 is, here we go, 2.125 times 10 to the 8 cubic meters. And so now I can just rearrange this to get time by itself. So divide by that 25, and I get 8.5 times 10 to the 6 seconds, which is quite a lot of seconds. But to be fair, it's also like a really large dam, and so this can last quite a while. Just to give you an idea of how many seconds that is, let's see. So that's basically, a couple thousand hours, or if you prefer, almost 100 days, actually. And so this could go on for a while. And of course, they could always pump water back into the reservoir if needed. All right, so pause there if you need to look at that some more. All right, so there is a problem um, having to do with pump storage on your practice worksheet that I would encourage you to try to work through on your own. If you would like, I can work through this during the next class, and the class after that is going to be your test. But I do want you to try to do question 25 on your own. This is actually, I think, the last free response question that you have on your practice worksheet. And so that's a question I want to take a look at together during our next class. Um, I would also highly encourage you to look at the problems in your textbook, the worked out examples, and also the problems at the end of the chapter having to do with pumped storage. And um, and as long as you keep the principles that I've been talking about in mind, you should hopefully be able to use your problem solving skills to answer these questions. All right, so as always, please let me know if you have any questions, and I'll see you guys in the next video.